Our insights for this deep dive are drawn from a comprehensive webinar titled Wireless Connectivity, Enabling the Next Industrial Revolution, which was prepared by the Alpert research team. This in-depth discussion explores the profound convergence of wireless communication with the fourth and fifth industrial revolutions, known as Industry 4.0 and 5.0. It moves beyond mere connectivity to reveal a fundamental reshaping of industrial landscapes. How are we structuring this deep dive today? We'll kick off defining Industry 4.0 and 5.0, what are their goals? Then we'll get into the wireless tech itself. From there, we connect the dots, real-world industrial applications. We'll also look at the challenges, the hurdles organizations are facing. And finally, we'll distill it all down into actionable strategies.
So, Industry 4.0, often called the fourth industrial revolution, signifies a monumental shift in how industries operate. It builds on a long history, right? Industry 1.0 brought mechanization with steam. 2.0 gave us mass production via electrification. Then 3.0 ushered in computerization and basic automation through IT.
Industry 4.0 takes all that much further. It fuses the physical and digital systems, like advanced automation, pervasive connectivity, sophisticated data-driven decision-making. Its core focus really is squarely on maximizing efficiency and productivity, aiming for mass production, but with minimal waste. Basically creating smart factories where everything's integrated and talking to each other.
And that's exactly where Industry 5.0 comes in. It's often called the fifth industrial revolution, but maybe it's better understood as the next evolutionary stage. It complements Industry 4.0, it doesn't really replace it. The European Commission defines Industry 5.0 as a vision that moves, and this is key, beyond efficiency and productivity as the sole goals. Instead, it explicitly reinforces industry's broader contribution to society. It puts worker well-being, environmental sustainability, and supply chain resilience right at its core. It's trying to leverage new technologies to foster prosperity beyond just, jobs and economic growth, all while respecting the finite limits of our planet. When we compare their goals and drivers, the differences become pretty sharp. Industry 4.0, as you said, its primary focus is deep automation, digitalization, optimizing for sheer efficiency, getting things done faster, fewer resources. Industry 5.0, though, shifts the paradigm quite a bit. The emphasis moves to human-machine collaboration, embedding societal goals, prioritizing sustainability and resilience. And this also fundamentally changes the human role. In 4.0, humans are often operators, monitoring, maintaining automated systems. But in 5.0, the vision is for humans to become active partners with technology, leveraging machines to amplify their creativity, do more value-added tasks, tackle complex problems machines can't handle alone. Industry 4.0 aimed for mass production with better efficiency. Industry 5.0 takes that further. It targets mass customized production, and with ambitious goals: zero waste, minimum cost, maximum accuracy. Its key principles are pretty well defined. First, human centricity. Humans do the creative, innovative stuff. Robots and collaborative robots, cobots, handle the heavy lifting, the repetitive, the dangerous tasks. That changes work itself. Second, sustainability. That means preserving resources, adopting circular production models, reuse, recycle, and seriously reducing energy consumption. And third, resilience. Focusing on boosting industrial production capacity while at the same time making it less vulnerable to disruptions from outside shocks like pandemics or geopolitical events. The urgency driving this shift towards 5.0 is, palpable. It's multifaceted. We've got huge societal challenges that demand circular production, rethinking energy policies. The pandemic, for instance, starkly showed us the need for robust, resilient supply chains that can handle shocks and adapt fast. For businesses, embracing Industry 5.0 means things like tapping new markets through hyper-customization, attracting talent by improving worker well-being, and critically, meeting those ever stricter ESG, environmental, social, governance targets. The implications globally are huge. Just look at Industry 4.0. It's projected to drive big productivity gains. Industry 5.0 aims to build on that, making industrial systems not just smart and efficient, but also more responsible, adaptable, and ultimately more valuable to society as a whole.
Now that we understand the what of these industrial revolutions, let's explore the how. Specifically, how are wireless technologies not just supporting this?
Wireless is no longer just, convenient. It's becoming indispensable due to several core imperatives. First, just consider flexibility and rapid reconfiguration. Wireless allows manufacturing lines to be quickly adapted or entirely rearranged with minimal disruption. Second, the seamless integration of mobile equipment becomes truly possible. Wireless connectivity liberates them, greatly enhancing their reach, versatility, and their ability to collaborate. Third, it enables truly scalable sensor deployment. Wireless can be easily added, moved, or reconfigured as production needs change without the prohibitive overhead of installing new wiring for every single device. And finally, it often leads to significant cost reduction. Now, there are certainly upfront costs with wireless infrastructure, but eliminating the need for extensive physical wiring cables, conduits, the labor for installation, maintenance can lead to substantial long-term savings. So, to reiterate, wireless is no longer a luxury or some niche alternative. It is a foundational enabler for the data-centric, flexible, and adaptive paradigm of both Industry 4.0 and Industry 5.0.
Okay, so let's dive into the specific technologies. What's the starting point, the cornerstone of modern industrial wireless today?
The cornerstone, undoubtedly, is 5G networks. 5G was really designed with industrial needs in mind from the ground up. It operates in 3 key modes, or service categories, each tailored for different applications. First, we have EMBB, that's enhanced mobile broadband. This mode delivers extremely high data rates. Next, and critically important for industrial automation, is URLLC. That stands for Ultra Reliable Low Latency Communications. This is the real game changer for mission-critical manufacturing. We're talking about guaranteed latencies below 1 millisecond that's faster than you can blink and reliability exceeding 99.999%, 5.9, sometimes more. Finally, we have MMTC, or Massive Machine Type Communications. This mode is specifically designed for vast IoT deployments. It's capable of connecting millions of devices per square kilometer with incredible energy efficiency. So the implication here is clear. 5G provides the required mix of connectivity, speed, reliability, and intelligence needed for the fourth industrial revolution to truly take hold and flourish. 6G is being designed to push capabilities far beyond 5G. We're talking aims for staggering data rates in the terabits per second range, near zero latency, potentially as low as 10 microseconds, and extreme reliability, targeting maybe 9 nines, 99.9999999% availability. But what's particularly exciting and truly fundamentally different about 6G is its expected native integration of artificial intelligence directly into the network architecture itself. This means AI won't just be an application running on the network, it'll fundamentally define how the network operates, allowing for autonomous decision-making, self-optimization, predictive resource allocation. Another pivotal feature planned for 6G is ISAC, Integrated Sensing and Communication. This is a breakthrough concept where the network itself becomes a kind of distributed sensor grid. It will be capable of not just transmitting data, but also simultaneously detecting motion, identifying presence, maybe even mapping object shapes or tracking positions within its environment. It will also leverage new frequency bands, including terahertz or T-hertz communications, opening up vast new spectral resources for unprecedented bandwidth. The implication for industry is profound. 6G will enable truly ubiquitous Industry 5.0 applications. It's about building a truly intelligent, omnipresent network fabric. Moving to more localized but equally vital wireless tech, we have the evolution of Wi-Fi, specifically Wi-Fi 6, 6E, and now Wi-Fi 7. These are crucial for dense, high-bandwidth applications right on the factory floor, often complementing cellular technologies like private 5G. Wi-Fi 6 brought significant improvements for performance in dense environments, exactly what a busy factory floor is. It achieves this through key technologies like OFDMA, orthogonal frequency division, multiple access. This allows multiple users with varying bandwidth needs to transmit simultaneously on different subchannels, really optimizing spectrum usage. It also employs spatial reuse, often called BSS coloring, which cleverly reduces interference by identifying and tolerating transmissions from neighboring networks. And MIMO, multi-user, multiple input, multiple output, also plays a key role, enabling multiple devices to communicate with the access point simultaneously. All this significantly enhances capacity and improves battery life, particularly beneficial for the many IoT devices in industrial settings. Then Wi-Fi 6E basically extends Wi-Fi 6's capabilities by opening up the 6 GHz band. It allows for much faster and smoother traffic flow, a major advantage in busy industrial settings where interference from older Wi-Fi, Bluetooth, microwaves, etc. can be a real problem. And the latest evolution, Wi-Fi 7, and marketed as extremely high throughput, pushes speed, capacity, and latency even further. It introduces game-changing features like multi-linked operation, or MLO. This allows devices to connect and aggregate data across multiple frequency bands, like 2.4 GHz, 5 GHz, and 6 GHz simultaneously. This dramatically improves performance, reduces latency, and increases resilience. It also supports much wider 320 MHz channels for higher peak speeds. And critically for industrial applications, Wi-Fi 7 is integrating time-sensitive networking TSN principles. This is a crucial step, bringing deterministic capabilities, guaranteed latency, synchronized communication, which were traditionally only found in wired industrial Ethernet, into the Wi-Fi world.
But what if you need to connect devices that are very far away, or that only send tiny bits of data very infrequently but need to last for years on a battery?
That's precisely where LPWANs, or low-power wide-area networks, come into their own. These are wireless networks specifically designed and optimized for long-range, extremely low-power communications. Their defining advantage is enabling battery-powered devices to operate for years without needing a battery replacement. This is invaluable in remote, harsh, or difficult-to-access industrial locations. LPWANs are optimized for transmitting small volumes of data simple sensor readings like temperature, pressure, humidity. Within the LPWAN category, there are several key technologies. You have NB-IoT, narrowband IoT, and LTM, also known as Cat-M1, which are part of the cellular IoT family. They leverage existing cellular infrastructure, offering good coverage and roaming capabilities. Then there's LoRa and LoRaWAN. LoRa is a proprietary radio modulation technology known for its exceptional long-range capabilities. LoRaWAN is the network protocol built on top. It achieves this long range by trading off data rate for sensitivity. The signal can travel further and penetrate obstacles better, even at very low data rates.
Now, what about even more localized sensor networks?
For those more localized, often very dense deployments, we turn to wireless sensor networks, or WSNs. These networks, built on various different protocols, enable distributed monitoring and control across, say, a factory floor or a specific process area. A variety of technologies fall under this WSN umbrella. For example, you have Zigbee and Thread. These are low-cost mesh networking open stand, also deployed in industrial settings for less critical tasks like building management systems, lighting control, or basic condition monitoring. Zigbee, for instance, can support mesh networks of thousands of nodes and operates in several frequency bands. However, they are generally less deterministic than specialized industrial-grade solutions. Bluetooth LE, or low energy, especially with its latest revisions including mesh networking capabilities, it can now support multipath peer-to-peer connections and reliable mesh networks. Especially in demanding environments, we have purpose-built standards like wireless HART, based on the HART protocol. These are designed for mission-critical applications, often in hazardous or harsh environments. They provide robust mesh networking capabilities for low-power sensors and are engineered from the ground up to offer strong reliability and determinism through sophisticated time-slotted scheduling algorithms. ISO 100.1.1a, while sharing many similarities in performance, offers potentially more network flexibility and greater support for standard IP-based networking. Non-terrestrial networks, NTN, and satellite IoTs. These are essentially hybrid networks that seamlessly blend terrestrial 5G and future 6G capabilities with satellite communication. They typically use constellations of satellites in low Earth orbit, LEO, or medium Earth orbit, MEO, which offer lower latency and higher bandwidth compared to traditional geostationary satellites. The fundamental objective here is to provide true global coverage, reaching remote areas that are currently unconnected or significantly underconnected by traditional terrestrial networks. It enables real-time management of global supply chains, connecting assets and processes even in the most remote locations. There is no single silver bullet wireless technology for Industry 4.0 and 5.0. Optimal deployment demands careful, application-specific selection, and, importantly, integration of multiple technologies. It's all about understanding the nuanced strengths of each. For instance, 5G shines with its low latency and high reliability for critical control tasks. LPWAN excels in low power and long range for widespread monitoring. Wi-Fi offers high bandwidth for local uses like video. The key is architecting a heterogeneous network, one that leverages each standard for its specific strengths, matching it to the application's requirements. This strategic integration, this careful balancing act, is truly key to unlocking the full potential of industrial transformation. Without this nuanced approach, organizations risk deploying solutions that are suboptimal, potentially limiting their whole digital transformation journey.
So we have this incredibly diverse toolkit of wireless technologies, but what does this all really mean beyond the specific standards themselves, the potential for Industry 4.0 and 5.0?
The sheer power and flexibility come from the sophisticated functionalities embedded within them. Let's start with 5G flexible numerology. It allows the network to scale the subcarrier spacing and the symbol duration in the radio signal. In simpler terms, it means the network can dynamically adapt its radio waveform characteristics on the fly. For example, it can use wider subcarrier spacing for high bandwidth applications where spectral efficiency is key, delivering more bits per hertz. Or it can use shorter symbol durations and narrower spacing for ultra-low latency applications that need minimal propagation delay and rapid signal processing. This flexibility is revolutionary because it optimizes resource allocation to meet vastly varying quality of service, or QoS, needs simultaneously. A single 5G network infrastructure can efficiently support a multitude of different industrial applications, each with highly unique and often stringent latency, bandwidth, and reliability demands. It can handle URLLC for robot control, EMBB for video analytics, and MMTC for sensors, all at the same time on the same physical network without compromising performance for any specific use case. Next, we move into the higher frequency bands. Millimeter wave frequencies, generally 24 to 100 gigahertz, are used in 5G. They offer incredibly high capacity and ultra-low latency, but usually over shorter ranges because the signals don't travel as far or penetrate obstacles well. Moving even higher, the T8 band, that's 100 gigahertz up to 10 telehertz. This band promises ultra-high data rates, potentially terabits per second, and extreme spatial reuse, meaning more devices can communicate simultaneously in a small area. Now, because of their very high frequencies, these signals have limited range and get absorbed easily by obstacles, even the air itself to some extent, but that characteristic actually makes them ideal for secure, high-capacity links within specific, confined zones of a factory. So these frequencies are critical for future applications needing massive bandwidth and extremely high-resolution sensing within defined industrial perimeters. Multiple input, multiple output. This technology employs a very large number of antennas to serve multiple users or devices concurrently within the same time and frequency resources. The core principle involves advanced techniques like spatial multiplexing and highly precise beamforming. The network can essentially create multiple independent spatial streams and direct radio energy very precisely towards individual devices. This minimizes interference between users and maximizes the signal quality for each one. The benefit is a significant improvement in spectral efficiency, meaning more data can be transmitted effectively over the same amount of spectrum, and a substantial increase in the overall network capacity and coverage. In dense, smart factory environments, massive MIMO is crucial. It drastically improves signal quality, reduces latency by ensuring more reliable and dedicated communication paths, and helps guarantee better coverage, even in complex and challenging radio frequency conditions often found in factories with lots of metal and moving parts. The evolution to multi-user MIMO extends this capability further by enabling multiple users or devices to simultaneously share the exact same time and frequency channel without significant degradation in performance, further boosting network capabilities for industrial applications and allowing a single access point to efficiently communicate with many robots or sensors. Beamforming is a sophisticated signal processing technique. Instead of broadcasting a signal in all directions, it precisely focuses the wireless signal towards specific devices, like a spotlight. This optimizes communication, reduces interference from other signals, and improves the reliability of links, especially in complex industrial settings with lots of metal and obstructions. Together, massive MIMO and beamforming are crucial for handling the immense traffic and precise communication needs in advanced manufacturing. The integration of time-sensitive networking, or TSN. Its fundamental principles revolve around achieving deterministic communication, guaranteeing bounded low latency, minimizing jitter, variations in latency, ensuring high reliability, and enabling precise time synchronization across the network. The exciting development is that these TSN principles are now being actively integrated into wireless technologies, most notably 5G, creating 5G TSN, and Wi-Fi 7. For 5G specifically, this means the 5G system can effectively act as a TSN transparent bridge. Ensure that time-critical industrial control messages, adhering to TSN standards, can traverse both the wired and wireless segments with guaranteed end-to-end latency and reliability characteristics. TSN integration fundamentally bridges the historical divide between the information technology IT world and the operational technology OT world in factories, enabling true industrial convergence and unified control over mixed wired and wireless networks.
How about tailoring the network itself to very specific needs within a single factory? Almost like having multiple dedicated private networks on demand, but using the same infrastructure.
That's precisely the promise delivered by network slicing, or NS. It allows for the creation of multiple independent end-to-end logical networks, often called slices, all operating efficiently on a common physical network infrastructure. Each network slice can be individually designed, deployed, customized, managed, and optimized to meet the specific performance and functional requirements, like latency, bandwidth, reliability, security, of various types of data services or different business operators or even different departments within a single enterprise. Each slice comes with its own guaranteed quality of service, QoS, ensuring that the diverse needs within a single factory, or perhaps even across interconnected sites, are met efficiently, securely, and crucially without interference or resource contention between the different types of traffic. It provides unparalleled customization and isolation of network resources. And closely related to network slicing and equally transformative for industrial users is the concept and increasing adoption of 5G LAN-type services and fully private networks. This involves deploying 5G networks, and potentially future 6G networks, privately. This means that an entire 5G system, including the core network functions, is contained within the logical and geographical boundaries of defined premises. This private network operates entirely independently from the public cellular network, giving the enterprise complete control over its operation, configuration, and data. It offers greatly enhanced security, as all sensitive industrial data traffic remains within the factory's controlled environment. It also provides unparalleled control and customization over network parameters, things like latency targets, bandwidth allocation, device prioritization, and security policies. Integrated sensing and communication represents a fundamental shift, a breakthrough where traditional communication functions, sending and receiving data, and sensing functions, detecting and characterizing the physical environment, are seamlessly integrated into a single system, often using the same radio signals and hardware. The network infrastructure itself becomes capable of performing both roles simultaneously. The transformative impact is that the network essentially becomes a kind of distributed, pervasive sensor grid. This allows it to do much more than just transmit data packets. It can also actively use its radio signals to detect motion, identify the presence or absence of objects or people, estimate distances and angles, map object shapes, or even track movements within its coverage area, all while potentially communicating data at the same time. ISACS essentially turns the network from a mere communication pipe into an intelligent, perceptive entity that understands its physical surroundings. Optical wireless communication, OWC, is also gaining some traction. Technologies like visible light communication, VLC, using LED lights to transmit data optical camera communication, and free space optical FSO links are being considered. They could be used for device-to-device communication or even for high-speed backhaul front-haul networks within a facility. OWC offers an alternative high-bandwidth, potentially very secure communication method for specific scenarios, especially where traditional radio frequency RF interference is a major concern, or where you have clear line of sight, like between two machines close together, or inside a clean room where RF might be restricted.
Okay, so we've covered the technologies and their powerful capabilities. What does this all mean when we bring it back to the factory floor, to the warehouse, to the actual supply chain? How do all these sophisticated wireless technologies translate into tangible value and real-world impact for industries, both right now and looking into the future?
These technologies aren't just theoretical marvels, they are actively enabling fundamental shifts across industrial operations and driving real measurable value. The Industrial Internet of Things, or IIoT. It's all about connecting physical devices, sensors, actuators, machines, everything from a tiny temperature sensor on a motor bearing to an entire complex production line to enable real-time data communication and control across the industrial environment. These devices overwhelmingly rely on wireless links. Maybe it's Wi-Fi for high bandwidth data from a machine vision camera, perhaps LPWAN for monitoring remote tank levels, or increasingly private 5G for mission-critical control signals to robots or AGVs. Wireless is needed to transmit that real-time data reliably. This forms the very foundation for data-driven decision-making, optimization, and automation. Wireless IoT is also essential for that flexibility we talked about, easily attaching sensors to mobile machines, reconfiguring sensor layouts, or monitoring assets in hard-to-reach places without running cables. It fundamentally automates the data flows that optimize scheduling, quality control, and overall throughput in smart plants. Digital twins are essentially dynamic virtual replicas of physical assets, processes, or even entire systems. It could be a single machine, a specific production line, a whole factory, or even a product out in the field. The key is that these virtual models are continuously updated in real time or near real time, with data streamed from their physical counterparts via sensors. To enable simulation, testing what-if scenarios virtually, monitoring, visualizing real-time performance, analysis, identifying anomalies or inefficiencies, and optimization, finding better ways to operate, all within a safe virtual environment before implementing changes in the real world. They require low latency, high reliability, and often high bandwidth wireless connectivity. Technologies like 5G or LLC or high-performance Wi-Fi like 6E or 7, potentially with TSN integration, are crucial. This ensures synchronous updates between the physical and digital and allows for high-resolution mapping and visualization, making the virtual twin truly reflective of the physical reality at any given moment. Edge computing involves processing data physically closer to its source right there on the factory floor. The primary benefit here is drastically reduced latency. This is vital for applications where speed and precision are paramount. Cloud platforms, on the other hand, provide virtually unlimited, scalable, and centralized resources for heavier, more complex analysis, long-term data storage, training sophisticated AI models, and performing global optimization across multiple sites or the entire supply chain. Wireless links are the critical connective tissue in this architecture. They provide the high-speed, low-latency, and reliable communication needed to seamlessly connect the physical assets to the edge devices, enable communication between edge devices, and link the edge infrastructure back to the central cloud platforms, and vice versa. They facilitate that localized data processing right where the action is, allowing critical decisions to be made in milliseconds, while also ensuring that relevant data is aggregated and sent to the cloud for deeper insights. Artificial intelligence algorithms and big data analytics platforms are essentially the brains that process and extract value from the massive data streams generated by these pervasive wireless sensor networks and connected machines. This enables powerful capabilities that transform industrial operations. Wireless technology is the fundamental enabler here. It's what reliably transmits this vast amount of diverse data, from tiny sensor readings to high-resolution video streams, from the myriad of devices on the factory floor to the edge and cloud platforms where these powerful AI and analytics engines reside. Without robust wireless connectivity, you simply wouldn't have the timely, comprehensive data needed to fuel these intelligent systems. Cyber-physical systems, CPS, characterized by a truly tight integration and feedback loop between computation, the cyber part, and the physical world, physical processes and objects. Pervasive, reliable wireless connectivity is the lifeblood of these CPS. It provides the constant stream of real-time environmental and operational data position, temperature, pressure, images, forces needed for the computational elements to understand the physical state and make intelligent control decisions. It also provides the channel to send commands back to the physical actuator. Wireless effectively blurs the traditional lines between human and machine and between the physical and digital domains, enabling this deep integration, fostering true human-machine collaboration, moving beyond simple coexistence to active partnership. The aim is to leverage the complementary strengths of both humans and machines. Humans are freed up to perform tasks requiring creativity, critical thinking, complex problem-solving, dexterity, or adaptability, while robots, particularly collaborative robots, cobots, handle the tasks that are physically demanding, highly repetitive, require extreme precision, or operate in hazardous environments. Ultra-reliable, low-latency wireless communication, like 5G URLLC or deterministic Wi-Fi, is the key technical enabler for safe and effective collaboration. It allows cobots and mobile platforms like AGVs to work safely and intelligently right alongside human operators, reacting in milliseconds to human movements, gestures, or explicit commands without the need for physical safety cages in many scenarios. This seamless, untethered interaction facilitated by high-performance wireless is what makes human-robot teams truly effective, flexible, and crucially safe. Augmented reality (AR) and virtual reality (VR) are rapidly moving from niche applications to becoming indispensable tools across the industrial lifecycle, and they simply wouldn't be practical or effective at scale without high-performance wireless connectivity. High-bandwidth, low-latency wireless connections, think 5G millimeter wave for its massive bandwidth, or Wi-Fi 6E7 with features like multi-link operation (MLO) for robustness, are absolutely essential for delivering seamless, high-fidelity AR/VR experiences. They enable real-time information overlays to appear instantly and track smoothly as the worker moves their head. They allow for high-resolution holographic telepresence, where remote experts can virtually be present and interact with local environment. And they ensure that these computationally intensive, immersive applications run smoothly without perceptible lag or motion sickness, which is critical for usability and adoption. Wireless essentially untethers these powerful visualization and collaboration tools. All of these technologies and applications converge in the realization of smart factories. These aren't just factories with automation. They are truly intelligent, interconnected environments where machines, sensors, systems, and even humans are constantly communicating and collaborating, enabling continuous monitoring, analysis, control, and optimization across the entire production process and value chain. Wireless connectivity in its various forms forms the very backbone, the central nervous system of these smart plants. It automates the critical data flows that are needed to optimize production scheduling in real time, implement sophisticated quality control measures, predict maintenance needs, manage energy consumption efficiently, and maximize overall throughput in ways that were previously unimaginable with siloed systems and manual data collection. Another direct and highly significant value driver enabled by wireless sensing is predictive maintenance. PDM uses smart sensors, monitoring vibration, temperature, acoustics, oil quality, etc., and sophisticated analytical techniques, often involving AML, to continuously track the actual health and performance of equipment in real time. Wireless predictive maintenance systems are key because they allow sensors to be easily deployed on critical assets, even rotating or mobile ones, to continuously transmit machine health data to central analytics platforms. Asset tracking and supply chain visibility are being completely transformed by wireless technologies. This involves achieving real-time or near real-time tracking and monitoring of goods, assets, containers, and vehicles throughout the entire supply chain. Technologies like LPWANs, LoRaWAN, NB-IoT, Sigfox are ideal for tracking assets over long distances with long battery life. Cellular IoT, NB-IoT LTM, provides broad coverage, often leveraging existing cellular networks. Bluetooth Low Energy, BLE beacons, are great for localized tracking within warehouses or yards. And even satellite IoT comes into play for truly global tracking where terrestrial networks aren't available. Wireless connectivity combined with automation and data analytics enables a fundamental shift towards highly flexible, mass-customized production. This facilitates on-demand manufacturing and highly adaptable production processes where products can be individually tailored to specific customer requirements without sacrificing the efficiency and speed typically associated with mass production. The seamless, real-time interaction between machines, and critically, the close collaboration between humans and machines, fostered by reliable wireless communication, creates the agility and information flow needed for this level of dynamic customization. Furthermore, wireless connectivity and the data it enables are fundamental enablers for entirely new product-as-a-service business models. Wireless provides those seamless, low-latency links needed between the physical assets, the edge processing devices performing immediate control and analysis, and the cloud platforms used for broader analytics, service provisioning, and long-term optimization, making these sophisticated data-driven business models feasible.
What are the key challenges organizations typically face when trying to adopt these advanced wireless technologies? It surely can't be all smooth sailing.
You're absolutely right. It's definitely not plug and play. While the potential benefits are immense, there are significant barriers and challenges that organizations must proactively understand and navigate to successfully implement and scale these industrial wireless solutions. The sheer proliferation of connected devices, sensors, actuators, machines, mobile robots, AR headsets in Industry 4.0 and 5.0 vastly expands the potential attack surface. So how do organizations address these formidable security challenges? There's no single silver bullet, but effective resolutions typically involve implementing comprehensive, multi-layered security frameworks. This often includes leveraging AI-based anomaly detection systems. Using lightweight encryption protocols suitable for resource-constrained IoT devices is crucial. Organizations are also starting to explore and plan for quantum-resistant cryptographic algorithms to prepare for the future threat of quantum computers potentially breaking current encryption standards. Furthermore, as we discussed, deploying private 5G networks offers an inherent security advantage by physically or logically segregating sensitive industrial data traffic from public networks. This is the challenge of compatibility across protocols and legacy systems. Manufacturing facilities are rarely built from scratch with all new equipment. They typically operate with a highly heterogeneous mix of machinery and control systems. Integrating these disparate systems with their different communication standards and data formats with new wireless technologies like 5G, Wi-Fi 67, or LPWANs is non-trivial. It's definitely not about finding one best wireless technology that magically solves everything for every piece of equipment. Instead, a strategic approach requires careful planning, understanding the specific needs of different applications, and often selecting and integrating multiple wireless technologies appropriately. The solution really lies in architecting a carefully planned heterogeneous network, leveraging the strengths of each chosen technology standard while implementing robust bridging and translation mechanisms. Often this is done through a phased modernization approach, tackling specific areas or applications step by step rather than attempting a massive, disruptive rip and replace. As we established, many critical industrial applications, especially those involving real-time closed-loop control, coordinated motion systems, or safety-critical functions, demand extremely low and, crucially, bounded latency, often consistently at the millisecond or even microsecond level. They also require incredibly high reliability. Wireless channel conditions themselves are inherently dynamic and challenging. Signals can be affected by movement of machines or people, interference from other radio sources, signal reflections, multipath fading, or physical obstructions, all of which can impact communication reliability and also affect the precision of time synchronization mechanisms. The integration of TSN principles directly into the MMK medium access control and PHY, physical layers of wireless standards like 5G, resulting in 5G TSN and Wi-Fi 7, is paramount. It focuses on developing advanced scheduling techniques to meticulously manage network resources and guarantee specific time slots or transmission opportunities for critical, time-sensitive traffic, ensuring it meets its strict per-flow latency and bandwidth requirements regardless of other, less critical traffic on the network. Ensuring energy efficiency for massive deployments. In large-scale industrial IoT deployments, particularly those using wireless sensor networks, WSNs or LPWANs for monitoring, however, replacing batteries frequently across potentially thousands or even millions of devices becomes incredibly costly, time-consuming, disruptive to operations, and often impractical or even unsafe. Optimizing energy consumption across these vast, dense networks is absolutely essential, not just for reducing operational expenses, but also for achieving long-term sustainability goals. The development and adoption of inherently ultra-low power wireless technologies, like the LPWANs we discussed, NB-IoT, LoRaWAN, Sigfox, are critical. These are specifically designed from the ground up to minimize energy consumption. Secondly, emerging wireless power harvesting. These technologies aim to capture energy from ambient sources in the environment like stray radio frequency, RF signals, indoor lighting, solar cells, thermal gradients, or even mechanical vibrations to trickle charge the device's battery or potentially power it directly, further extending operational life or even eliminating the need for battery replacements entirely in some scenarios.
We've certainly journeyed through a fascinating and complex landscape today. We've gone from the foundational shifts of Industry 4.0 and the human-centric, sustainable goals of Industry 5.0, right through to the intricate web of wireless technologies 5G, 6G, Wi-Fi, LPWANs, and more that are making it all possible. And importantly, we've also faced the very real challenges: security, compatibility, determinism, energy, spectrum, that demand our ingenuity and strategic thinking.
It's a dynamic and rapidly evolving field. To perhaps summarize this transformative journey, and borrowing from the conclusion of the Alpert research team's work that guided our discussion, Industry 5.0 is no longer a futuristic vision. It is an evolving reality, and wireless communication is the enabler at its core. Organizations that proactively embrace wireless innovation will unlock smarter production systems, resilient supply chains, and sustainable human-centric value creation. As the industrial landscape continues its shift toward autonomous, intelligent, and adaptive ecosystems, the speed and sophistication with which enterprises adopt and integrate wireless technologies will determine their long-term competitiveness.
That's a powerful concluding statement from the Alpert research team, really underscoring both the urgency and the significant opportunity of this moment in industrial transformation. So, as you reflect on everything we've discussed today, the potential, the technologies, the challenges, perhaps consider how your own organization is preparing for this profound shift. Are you, or is your organization, merely observing these changes from the sidelines, or are you actively and strategically planning how to integrate these wireless innovations to define your future competitiveness, enhance your resilience, and truly embrace a more human-centric and sustainable industrial future? Hopefully, this deep dive has armed you with some of the essential knowledge and context needed to start asking those crucial questions within your own teams and begin charting your course in this exciting new era of connected industry.
If you're interested in a deeper understanding of this transformative shift, we invite you to explore Alpert Research Team's presentations on wireless connectivity technical aspects and other related issues and aspects.